So good morning, everyone. On behalf of my program co-chairs, Anat Levin, David Lindell, Renning, and myself, I would like to welcome you to ICCP 2025. So I'm sure you're just as excited and anxious about listening to research talks and not me, so I'll try to keep my remarks brief. Basically, I want to highlight three things. One is the people who helped make this happen. Secondly, I wanted to point out a couple of new initiatives that we brought into ICCP, and finally, just give you some basic, logistical information for finding your way around the conference. So first of all, this would not have happened without a fantastic team. Aditya Pediredla and Ashwin Sankaranarayanan for finance, Chi Guo and Emma Alexander for poster and demos, Vivek Buminathan for publications, Felix Haide and Cecilia Zhang for industry chairs, Costa Drepanis and Rimin Chao, social media, and Ilya Chugunov as a website chair. And really, the fact that we're here today, extremely hard work of the local arrangements chairs, Jasmine Diaz, Esther Lin, and Sotiris Nusias, who, Sotiris and Esther, if you're around, can you please stand up for just a second? So Esther is over there. Where's Sotiris? Yeah. And of course, a strong set of very conscientious volunteers who should be wearing a t-shirt like mine, so you should be able to see them around. Are you guys here? Okay. In fact, a lot of them are busy outside trying to make sure that everything works well for all of you. Okay, now highlighting a couple of new initiatives here. The first one is that we decided as program chairs to slightly change the format and significantly expand the set of invited speakers so that we don't just get strong, discrete research results presented at the conference, but also we can get a broader overview of some of the latest research in computational imaging across many disciplines, and even though that may have been presented in many different venues. So I hope you find the program exciting and stimulating. The second initiative is something that has already happened. So for Saturday and Sunday, the 2 days prior to the meeting, we had our first computational imaging summer school. So this was a school where 25 students participated in several hands-on sessions. They received travel stipends to be able to come, and they participated, and we had essentially 4 broad sessions in computational imaging that, with instructors that you see here and the topics that you see here, that were covered over these 2 days. And this really wouldn't have been possible without the leadership and initiative of Katie Booman and Yanis Gulekas, who really developed the entire program, recruited the instructors, handled all the student applications, and so forth. So if you want to hear more about this, please find Yanis. I don't know where he is. Maybe he's not here yet. But please talk to Yanis, and we hope this is something that will continue and potentially expand in future years. And moreover, spread the word. Okay, spread the word and talk to your to students apply next year. So lastly, this would not be possible without the strong support from our industrial sponsors, both our gold sponsors as well as silver sponsors, who really provided very significant financial support this year, but as also many of them have supported us for many years in the past. We would also like to acknowledge the gracious support of NSF, which provided a significant part of the travel awards for students in the summer school, and of course the IEEE Computer Society. And lastly, I would like to thank the Daniels Faculty of Architecture, Landscape and Design, who graciously made this space available to us. And I really hope you can explore this space and see how wonderful it is, and how wonderful an addition to basically the heritage of Toronto as a whole. Now, just for a couple of logistics, we don't have any printed programs. You can use this code to grab the program online. Demos, okay, and posters, they are on the right, okay? So you use the right door to go to the poster area. There are posters going to be set up along 2 corridors on the first floor where we are at, as well as the second floor. The demos are upstairs. Follow the signs, you'll be able to find them. The reception today is a 5-minute walk from here. It's at 7 o'clock. Instead of giving you detailed directions, we just have this QR code. It's just Google Maps. It'll tell you how to get there. We're organizing lab tours during the reception today, so you need to sign up by 2 p.m. at the registration desk if you want to join. There are only 30 spots available, so you better, if you're interested, you better sign up soon. And the tours will leave from the reception area, so you can just go there and grab a drink or something to eat, and then go on the tours. And finally, for the banquet tomorrow, again, these are the directions. It's about 15 minutes from here walking. So that's it for me. I'd like now to hand it off to David Lindell, who's going to talk a little bit about the review process, and then finally to Anat Levin, who will do the award announcements.
Thanks, Kiros. So I'll say a few words about the review process for ICCP this year. We had 67 submissions, which is a 40% increase from last year. 14 of those were accepted to the ICCP proceedings, and 10 papers were accepted to transactions on pattern analysis, IEEE transactions on pattern analysis and machine intelligence. 6 of these TPAMI papers were forwarded to an awards committee, and ultimately 2 papers were selected for an award, and we'll hear more about that very shortly. This year was the first year that we tried using Open Review. The Open Review system has been adopted by major computer vision conferences, machine learning conferences, and we decided to try it for ICCP. So if you have feedback about Open Review, you can come up to me and chat about that, about how you thought it went, or if you have any suggestions for future years, I'd be happy to collect that. The process went as follows. We had the program committee, our reviewers, bid on papers that they weren't conflicted with to review. And then we assigned, the program chairs, we manually assigned 3 reviewers per paper, and we ensured that each paper had at least 1 senior researcher assigned to that paper. As far as managing conflicts among the program co-chairs, the program co-chairs did not submit papers. We also followed reviewer consensus. We came in and handled disagreements for papers where there was no consensus. We came in and managed that and helped to make the decisions. And we also made all the conditional TPAMI accept decisions. Then all papers that were conditionally accepted, either to ICCP or to TPAMI, underwent an additional shepherding round where one of the reviewers made sure that all the requested revisions were incorporated into the paper and then ultimately gave their approval. And then the final TPAMI decisions were also confirmed by 2 TPAMI associate editors, Gordon Wettstein and Hajime Nagahara, and we'd like to also thank them for their help with this process. So now I'll hand it off to Anat to go over the awards.
Okay, so we go to the most exciting part. So before I actually present the awards, I want to thank the Best Paper Award Committee, which is Wolfgang Hidrich, Ashok, and Matt O'Toole, and Todd Zickler, who actually reviewed all the award candidates and made the decision. Okay, so we have two winners, a honorable mention and a best paper award. So the honorable mention goes to depth dynamics via 1-bit frequency probing in embedded direct time-of-flight sensing. So I hope one of the authors is here. And then the best paper award is centroiding point objects with event cameras by Connor Hashami and co-authors. Do we have them here? So welcome to ICCP.
What's that?
I said welcome to ICCP. Are we done here?
Yes, so now we, I guess, are not only on track, but a bit early. So we have 5 more minutes till our first keynote speaker. You want to start now? You want to introduce?
Yes. Okay,
okay,
so
let's do
we move to our first keynote speaker. Our keynote speaker is Austin Roorda. And Austin Roorda received his PhD from the University of Waterloo here. And just recently he returned to Waterloo after about 30 years. And during this time he made tremendous impact to the research of vision science. So he was a postdoc at Rochester, a faculty member at Houston, and then a faculty member at Berkeley Vision Science for 20 years. And he really made a tremendous impact about the field of vision science and the study of the eye structure. He pioneered the research of adaptive optics in vision science, which was used to really study the cone structure and the color sensing. And then he also pioneered the use of laser scanning technology in which we can use laser scanning to actually influence the way the cone, the way that we sense light. And he received numerous awards for his work. And I won't review all of the awards that he got because I think that it's more interesting to hear from him than to hear from me. But please welcome Austin.
Okay. That's yours. Okay. Well, thank you. Okay, bear with me for 1 second. Okay, here we go. Well, thanks for the invitation, first of all, to the organizing committee. It's here at an international conference, which now becomes not so international for me. But I did grow up in Southern Ontario. I did my undergrad and PhD at University of Waterloo, as mentioned. And now 30 years later, I'm back at the University of Waterloo. I've been there for 2 weeks. So everything I talk about today, even though I think I'm contractually obliged to put Waterloo on the title, I'm wearing a Waterloo t-shirt underneath this one. Everything's done at UC Berkeley. And some of the preceding work, of course, done at Houston and Rochester. Okay, so I'm a vision scientist. I've actually been to this meeting. I was at this meeting in 2013, and I think they either invited me because they remembered my talk in 2013 or because they forgot that I gave a talk in 2013. I'm not sure, but it's exciting to be here. So I'm not really a computational photographer, whatever that means. But if there's any computational process that we should be interested in, one of the first ones ought to be vision. And what compels me to study vision? Well, it's this question that how does this cone mosaic, we got a tiled cone mosaic in the back of our retina, that is the first stage of processing vision and yielding the percepts that we have. And it's for at least for daytime vision, we use our cone photoreceptors, and they come in three flavors, sensitive to reddish, greenish, and bluish part of the spectrum is illustrated here. This is a false color image of what the colored cone mosaic might be. And interestingly, this is the mosaic. It's kind of random. The proportions actually vary quite a bit between individuals, and yet we immediately, effortlessly, and accurately generate very good percepts of color when different spectra, images of varying spectra land on this sensor. And at the same time, we see our vision, our spatial vision, pretty much works at the Nyquist sampling limit of the photoreceptor array in our fovea, our foveal center at least. And we do this despite the fact that when I ask a subject to fixate steadily on an object, or if your optometrist asks you to read and look carefully at the smallest letter on the acuity chart, your eye is constantly moving, right? That is a fixating eye on the right, looking at a letter. And despite that motion, we see at the sampling limit of our photoreceptors. And so this is what has kind of motivated the research that we do. So the title is Oz Display. I'll go back. And my co-author is Renan, who apologizes that he can't make it to the meeting today. He's actually has been in Malaysia for a couple of months, so he wishes he could be here. I wish he was here. And he's a deserved co-author on this paper, this presentation, as you'll gather when I go through the talk. But it's been really my whole life's career, weirdly, that led to what I'll finally talk about today. It's not that I was thinking about some of these final results for 25 years, but it is an evolution of a system that enabled some of the experiments that I'll end up talking about. And it really started, my motivation when I started as an academic, essentially, was to build and design optical systems that could reveal the structure of the retina, take images of the retina on a very fine scale. And the specific platform that I used is called the Adaptive Optics Scanning Laser Ophthalmoscope, or Scanning Light Ophthalmoscope. And it's an imaging system that probably many of you know this, but it doesn't record an image in a conventional way by casting an image onto a sensor, onto a 2D sensor, but it builds an image over time, pixel by pixel, line by line, frame by frame, by recording the returned light from a focused spot as it scans across the retina, just like a scanning laser microscope. It's a point scanning system. And you'll learn over the next 4 or 5 slides why this is a platform that's especially useful for the kind of research that I'm going to describe. So first of all, the eye's optics are one of the first barriers to studying the structure and function of the human retina, trying to ask the questions that compelled me to do vision science. And the optics are, although they're fine for vision, they're actually kind of crappy compared to what they could be, right? They're not even close to being diffraction limited. And so in order to just see the cells and get a view of what's happening in the back of the retina. You have to use adaptive optics in your imaging system to measure and compensate for those imperfections in the cornea and the lens that blur the image. And this just shows a scanning light ophthalmoscope in action, adaptive optics off, adaptive optics on. It's a live image of the human retina. It's about 1/3 of a millimeter across. You'll see that this is an eye that's asked to hold their eye still, but it's constantly moving. All the small dots that you see in the image is the light scatter from a single cone photoreceptor. So what you're visualizing is the mosaic of photoreceptors. Cone photoreceptors are the light sensing cells in the back of the eye. There's a couple of other things you can see. You might see things wiggling across the field. Well, in front of the retina in a human eye, that's where the retinal blood vessels run. And so these are single blood cells coursing through the capillaries that are running in front of the retina. Okay, so adaptive optics, scanning light ophthalmoscopy allows us to get a microscopic view of the retina. This has been really useful for me throughout my career because we've used these tools to image patients and to look at patients with eye disease on a very fine scale. But a scanning system is not only useful for recording an image of the retina, but it's also useful for delivering an image to the retina. So imagine now, I'm using red light to form an image of the retina. It happens very fast, 30 to 60 frames per second. So if you were a subject in my system, you would just see a red square. Now, if I modulated that laser that's producing the red square in such a way to, say, cast a letter E on the retina, turn it off at the appropriate time points, then the subject would see a black letter E in a red square. Okay? Now, if I turn off the laser that's forming the image, that pixel doesn't record any light. So the letter E that you see in the video is not an overlay of an E onto the video. That's the actual video that you record. The stimulus gets encoded directly into the video that's recorded. And so now you can begin to appreciate how this might be a very useful tool for not only studying the structure of the retina, but its function. So even in a video like this, if I ask the subject what the letter is, or what the orientation of the letter is, I can see what cones interacted with that letter. I can see exactly how the eye moved over the time course that it took them to make the decision. So we can really learn about these visual processes. But now if you were looking at a spot like this, a dark spot, so when I think about clinical applications, I think about, well, what disruptions have occurred due to this mutation or whatever in the retina, and what are the functional consequences of those? So there's a dark spot here, and I might think, okay, well, I wonder if that cone is just not reflecting very well, or it's a dead cone. And if you want to test function on that kind of scale, well, then you have the problem that the eye is constantly moving, right? You're trying to track a moving target. Many of you people know this. The problem, or a phenomenon, let's call it, with scanning systems, is that if you scan a moving object, the image of that moving object is not blurred, but it's distorted. Now, some of you may have heard of a photocopier before, but if you're in a photocopy room and you're recording, trying to make a photocopy of a paper, and somebody bumped into you, then you would see that event in the image that you recorded of that page. It's not a blur, it's a distortion, and the distortion tells you exactly how much you moved the page and when exactly you moved the page, because time goes from top to bottom in the recording. So, like I said, for me it was a problem because I was trying to take distortion-free images of the retina, but for you it's an opportunity, and many people realize this, of course. The rolling shutter effect has been used by probably many of you in the audience to extract motion in other signals. So in a scanning system, and a scanning imaging system, Jeff Mulligan in particular just wrote a very nice paper articulating the problem and the potential solution. And so these images are scanned, they're distorted, and we want to correct for those distortions. And the way you do this is you get a reference image. Let's assume it's a undistorted free or distortion-free reference image. Every image that you acquire of the moving eye will be sheared and compressed and expanded due to the eye motion. But if you break it up into strips, you can register the strips with the reference image here, and you can generate a distortion-free frame. If you do this on every frame, you can generate a distortion-free movie. And it's very accurate because it's correcting for motion on the scale of a single cell. So it's an eye tracker that has micron scale resolution. This, to me, was important for generating distortion-free images of the retina. But the byproduct of that correction, of course, is an eye motion trace. And with the help from a lot of very good engineers and computer scientists, we not only solved this problem for offline processing, but we solved this problem for online processing. So while we're collecting an image in real time, we're constantly measuring where the eye is, and we're using that information then to guide the delivery of a stimulus to lock it on a target or to move it in ways that are entirely programmable and controllable by us. And so we take the eye motion information, we utilize the same tool for delivering a stimulus to the retina, and we control the stimulus position or the timing in a way so that we can pin the image directly onto the retina. So again, this is a video, this is not an overlay of a letter that's stabilized on the retina. In fact, you can see a little bit of wiggle of that image, and that wiggle is because of latencies and errors in the tracking process, but the standard deviation of that wiggle is a little less than the size of a cone. So we can control the position of a stimulus that we place on the retina to the scale of a single cone photoreceptor. So now we can start asking very specific questions about how the cones on their own may mediate vision. Now this is done by using a red light for imaging and turning off the red light to put a decrement so the subject would see a black letter E on a red background. That's useful for a lot of things, but we're interested in delivering positive light like bright stimuli to cones. And so in order to do that, it's just a matter of adding extra wavelengths into the system. So now we can build a scanning laser system that uses near-infrared light to scan an image to the retina. So it's almost like covert imaging and eye tracking. And then instead of turning off the laser to present a dark spot, we can turn on a second laser to present a bright spot. And this is just an illustration of that, where this is, of course, not the video that's being recorded anymore, but it's an overlay of a digital overlay of a green spot onto the retina. But we can image and track the retina covertly and then deliver images in exactly the manner that we want. And this was many years of work. There's a lot of problems to solve. The eye has a huge amount of longitudinal and transverse chromatic aberration that we have to solve. Those things were not easy, but we were ultimately able to see the cone in infrared and lock and deliver the stimuli to that targeted cone or that specific cone with whatever visible light we chose to integrate into the system. In this case, it's 550, I think, is what I've illustrated here. Now, that's about where we were at in 2018. And we did a lot of experiments. We did single cone psychophysics. I could measure the sensitivity of a single cone. I could measure the color sensation elicited when you stimulated a single cone. And we were very proud of ourselves. But I went to a conference like this. Reneng was in the audience, and he said, well, why don't you just do all the cones? And I said, well, that's hard. I mean, yes, of course we'd be interested, but it's computationally very difficult. And of course, he knows about computation. He knows how to solve those difficult problems. So since 2018, we teamed up with Reneng, and I call it his army of computer scientists. Even Emma was there for a period. And since 2018, and with help from them, we not only can track and target light to one location on the retina, but we can track and stimulate all the cones across the field, up to about 5,000 cones per frame at 60 frames per second. And so I can brag about it because I didn't do it, but it was a very impressive advancement that they enabled. And so that became the Oz Vision display, which we call a new principle for visual display. And it's really in the sense that we can deliver visual signals, not to the retina, I should say visual signals to the brain via the retina at the level of the photoreceptor. So This kind of display bypasses constraints that are imposed by the optics, because we can use adaptive optics to sharpen the image. It bypasses constraints imposed by the natural eye motion. And it even bypasses limits imposed by the cone's spectral sensitivity, as I'll describe moving forward. But let's step back a little bit before I get into some of the experiments enabled through the Oz platform. I'll step back just a bit to talk about an earlier experiment, just to give you a feel for the kind of experiments and the kind of experiments that we can do. And this is a fairly old study, but it's one that I like, and it's one that's easier for an audience to digest, especially this audience. And it's about the benefits of eye motion for spatial vision. So as I showed you, we can see at pretty much the Nyquist sampling limit of our photoreceptors, despite the fact that the eye is constantly moving. We perceive the things that we look at as being stable. So not only are we able to manage that motion, but we somehow suppress it in our percept. We're not aware of the motion that occurs, even though that kind of motion our visual system is exquisitely sensitive to. But here's a really simple question. Are they beneficial for acuity? Are they just a pain that we've evolved and developed ways to overcome, or can we actually leverage that information? So the question is, if I was to do a letter identification task where I let it naturally move, which is the left panel, or had it actually pinned onto the retina, which is the right panel, which one would under which condition would you do better? And some of you may know that the visual system works in such a way that if you were to stabilize an image on the retina, it would fade from view. It takes a little while to fade from view. So before it fades, you can see it, but it'll fade. So we controlled for that fading as being a factor. So these two conditions were equivalent in the sense that we mitigated or controlled against the fading. So then we just compared an identification task. In our system, we do a 4 alternative forced choice tumbling E task. If you're in the system, you're actually in a bite bar locked into the system to hold your head still. And so you can't read off a letter chart. So a common way to do vision experiments in our system is to just use a key press and have them identify whether an E is pointing left, right, up, or down. 4 alternative forced choice tasks, and you just find the letter size or the conditions under which they could do this at some percentage correct. And so we made the letter very small. We made it so that it was above chance. So if you're just guessing, you're going to get it right 25% of the time. So we got them to a level. We made the letter small enough so that they got it correct about 50% of the time. And then we compared that same letter size between the natural and the stabilized condition. So, all right, who thinks you're going to do better under natural viewing conditions? Put up your hand. All right. And who thinks you're going to do better under the stabilized condition? Put up your... See, of course, this audience is, except for one person. You're brave. Yes, there's one person. So, of course, this audience thinks, all right, well, a computer can do it. Why wouldn't the brain be able to do it, right? So the answer is the first one. So 97%, 99% correct. And that if you let it naturally move, not only do you see it as being stable, but you actually do a little bit better. So these are 4 subjects, and the percentage correct of the purple bar was a little better when it was naturally moving versus when it was stabilized. And I don't have to explain to this audience what the intuition about this, but this is a letter that it was actually a little bit below the Nyquist sampling limit. And if you looked at a sampling of this letter in a static representation, represented it as a Voronoi tessellation, well, you're going to have some difficulty judging. There's 4 letter E's encoded by these 4 patches. And if I did a poll of the audience, which I won't do, it'll take too much time. But we would be probably a little bit above chance in guessing which E's are encoded, what 4 orientations are encoded by which patch. But if I just take the patch and dynamically change it by moving the patch behind the letter, then it becomes quite obvious, right? I think 100% of the people will judge the orientation of the letter correctly in these four, and if you're not sure, those are the answers. So this is the kind of experiment that we've been able to do with our system and learning something about the structure and function of the visual system. And so like I said, I haven't been working for 25 years toward one project. We've done a lot of small projects along the way that were enabled at that time by the technology that we had. But really, the Oz Vision project is the one that I want to talk about, that we're currently very excited about. And this is the one where we really can control the activity of every single cone, at least within the small field that we can image and track. But we'll start with a small thought experiment. You're looking at a red patch. Let's assume it's 600 nanometers. And that red patch at any moment would be landing on your retina, which is a mosaic of 3 cone types. And we know the spectral sensitivity of the cone types in the eye. They're fairly consistent between everybody. So if it was 600 nanometers, I could predict exactly the degree of excitation of each one of the cones in the mosaic. And so I could represent what I would call the photoreceptor outputs, or the excitation levels. Now this is what gets sent to the brain. Right? So the brain gets this information and it has to make sense of it to yield the ultimate percept that you have. So what would the brain see when it's given these inputs? Well, does it see a luminance variation and then infer from that specific luminance variation that it's probably red, and then it sort of paints the scene as being red? Oh, the answer is no. Nobody sees that. Nobody saw that when I showed the red square. What you do is you immediately and effortlessly and accurately generate a percept of uniform color. Okay, so that's a surprise. Now that I explained it to you, you go, holy cow, okay, really, we have to do that. That seems like a complicated process. All right, well, people spend their careers trying to figure that one out. But here's the part of the experiment. Now, if I just used a different color light, but patterned it, I could use a different color light, pattern it in such a way to generate identical photoreceptor outputs. And so what would you see under those conditions? And the answer is you have to see a uniform colored square, because the brain doesn't know anything except what gets sent through the optic nerve, and that's it. That's the photoreceptor outputs. So this is what we call spatial metamers, spatial variations that are metamers or replacements for color vision. And this is just a simple example, but here's a more sort of real-world example. When you look at a dynamic like a cartoon, here the Elmo video, what this does is it's constantly dancing across your retina as you're making saccades or just fixating the fixational eye movements as you're looking at the target. But you can look at the individual RGB values per cell, landing on each cell, and you can map that against the specific cone types that those RGB values are landing on, and then you can calculate exactly what microdose I have to send to that cone to achieve the same photoreceptor excitations as the natural video would have produced. So we can easily calculate what the microdoses would have to be for any wavelength, by the way. I can use any wavelength I want. So this is specifically calculated for 500 nanometer light, and this is exactly how much a grayscale code for exactly how much I would have to tickle each one of those cones in the mosaic to achieve an identical photoreceptor output or an identical optical signal that I would send from the eyeball to the brain, right? So this is the Oz Vision principle. We've looked at these videos. They do look colorful. We can't really quantify the experience, so I'll talk about some basic experiments that we've done to sort of prove the principles here and validate the principles. Everything we do is on human eyes. And in fact, this is a picture of my eye. There's a small patch in my eye. I travel to the University of Washington where they can map and classify the cone types. That itself is not so easy to do. But this is a patch of my retina over which my cone types have been classified. And so we would take, and there's about 7 or 8 subjects now that have been involved in these studies. And so we take these cone mosaics, and now we can play the cells in these cone mosaics to generate these color signals that we can send from the eyeball to the brain. And so here's just a movie that just shows a typical video of a moving eye. So while we're viewing the video, the software is constantly monitoring where the eye is, and it's constantly then. This is just a map that is a color overlay that illustrates the fact that we can track, we know which cone type is which, we can track each cone type, and then we have systems while the beam is scanning to deliver the microdoses in the exact amounts that we would like to deliver. And so one of the initial experiments that we wanted to do with this platform was to study color in exactly the way that I had described before. So we can, for example, just track only the L cones, the reddish sensitive cones, and stimulate only those. Or we can track only the M cones, or the middle wavelength sensitive cones, and stimulate those. Or the S cones, which are quite sparse, the short wavelength sensitive cones, and stimulate those. And under those conditions, we recorded what the color appearance was. The idea being that if you stimulate only the L cones, you should see red. M cones, you should see some version of green. And S cones, you should see some version of blue. So how do you plot color appearance? So let me just show you. This is the Maxwell triangle. This is maybe a little less familiar to you than conventional color space drawings or renderings. But this shows the relative excitation of the S, M, and L cones here on what's called a barometric plot. And within there's a colored patch, and that represents the gamut of human vision. It kind of looks like a twisted version of the CIE color map. And why doesn't it fill this whole space? Well, the reason this is the color gamut and it's not the whole triangle is because of the spectral overlap of the cone types. So the M cones are sandwiched between the L and S cones. And so there's no way you can excite those on their own because they spectrally overlap. So there's no wavelength in nature that can stimulate only the M cones. And so as a result, the human gamut, the human visual experience can't get into this space, right? So that's why it's constrained to a smaller portion of this triangle. Now, if the cone types were completely spectrally distinct, that might be a different case. But this is a constraint really imposed by the physiology of the human retina and nothing else. All right, so when you stimulate only the L cones, all right, sorry, standing in the way. If you stimulate only the L cones, then we're using 543 nanometer light in this particular set of experiments. 543 happens to be a wavelength. It's greenish, but it's equally sensed by the L and the M cones. So the green wavelength that we use to stimulate is shown here, that little green square. But when we stimulate only the L cones, the patch, the square patch on which the light's being delivered goes from a greenish to a distinctly orangish or reddish appearance. Not perfectly red because the technology is not perfect. Okay, now some of you may be thinking, what a colossal waste of money. If I wanted to let someone see red, I would just show them red. This is the most expensive, inconvenient way to make someone see red. And you know, this is why the government's cutting all of our funding for wasteful and fraudulent. Okay, so why is this interesting? So now I'll explain why we're interested. Well, I already alluded to this space here, this unreachable space because of the physiological constraints of the three cone types. But we're interested in colors beyond the natural gamut, and we're interested in how the brain is going to even handle this new information. And so this is the question: what happens when you stimulate only the M cone, something that natural light could never do, but by spatial isolation, tracking and targeting of the light to those cone types, we can do something that natural light could never do. And just to make the point a little clearer, these are the spectral sensitivities of the photopigments of the photoreceptors S, M, and L. And you see they overlap, M and L overlap almost 95%, and the S is distinct, but still there's no wavelength that can stimulate only the M cones across the spectrum. All right. So the potential gamut, though, with the Oz display is that we could target and stimulate individual classes unconstrained by their spectral sensitivity. So whereas this is the normal gamut, the kind of gamut that we may be able to achieve with Oz display fills the entire triangle. And sure enough, when we did this experiment, when we stimulated only the M cones, we ended up with a deep, rich, saturated blue-green color appearance. That when we compared it, we do very quantitative color matching. When we compared it against the natural light that appears the most saturated, which are the ones that lie on the edge of this gamut, which are generated by monochromatic wavelengths. They're the spectral colors, so-called spectral colors. So we bought a supercontinuum laser where we could dial up its wavelength to get the best hue match. But when we compared that patch of light to the Oz display patch of light, of only M cones, that patch of light like literally paled by comparison. And the only way to do a quantitative match was to dilute the color elicited through this sensation to bring it down to look like a more natural light. All right. This was a color, and if you are on TikTok, you might have heard of it because this is the one we called OLO. We called it OLO because it's 010SML, and It got a lot of attention. But in a way, it's kind of a proof of principle of our technology. How much time do I have? I have about 10 minutes. Is that right? What time is it? Okay, good. 10 minutes is good. There's a little debate, a healthy debate about, the title of the paper was novel color, the first two words. So we said, it's a new color. But I described it. I was a subject, so I could see it. I say, okay, that's like, it was pretty profound, deeply saturated. It was really exciting when I had to dilute it to make it look like a natural color. But I could describe it. It wasn't like an otherworldly experience that I can't describe to you. So is it a new color or is it not a new color? Here's what I was just telling Emma this morning. Well, everyone agrees that red is red and pink is pink. Nobody thinks pink is red and nobody thinks red is pink, at least in the English-speaking, maybe Western world. Those are distinct colors. And the distinct colors are the only difference between red and pink is saturation. So the only difference between OLO and the blue-green color that we described it as is saturation. And now, if you're a baby, you might not even see colors properly, but as you start to see colors, you might distinguish reddish hues from greenish hues from bluish hues, and it may be only over time where you develop a distinct, your percept refines in a way to say, okay, yeah, pink and red are really different. These things take time in childhood, just like stereo vision and spatial vision. A lot of visual processes take time to develop in childhood. And so while today, and when we did these experiments, we can describe the colors, my contention is that if exposed to this long enough, I would say, okay, I don't think the blue-green that I called it before is doing it for me anymore. We're going to have to come up with a new name. And by the way, it's not here, and that's because there is a lot of leak. So even though we use adaptive optics to focus light onto the cone, there's a little bit of spread due to scatter in the optics. There's also a lot of spread, so after the light goes through the cone, it goes in to the rest of the retina and scatters around. And so even though our optics are as good as they can be, the percept is not entirely M. But it sits decidedly outside of the gamut. Okay, so in the last bit of time, I'll talk about what we're thinking about, and one of the reasons why really we're interested in this is because years ago, 2009, there was a group, Jay Knights at the University of Washington. They did a gene therapy to add a third cone type to a squirrel monkey that was dichromatic. So dichromatic means you only have two types of cone, short wavelength sensitive and long wavelength sensitive. but they administered a gene therapy that would give them a third cone class. And they trained the monkey on an experiment to differentiate, just basically doing a color chart like the Ishihara color chart, a version of that, where they could differentiate colors. And at the beginning, they had them very well trained on the task, but the dichromatic squirrel monkey could really not distinguish between red and green, just to put it simply, because they were dichromatic. And after the gene therapy kicked in, after the opsins started being expressed in the photopigments, they started doing the task. And that was a big discovery. But the big question was, what did the monkey see, right? What did the monkey use? All they were doing was discriminating two colors, but did they really see a new color? Or was there some other sensory input, like some sort of scintillation conferred by this new cone type? In other words, did they perceive that luminance variation that I described before and use that as a cue to do the judgment? And you can't know. You can't ask the monkey. Of course, you would not do the gene therapy in a human unless you knew it was going to yield some benefit, because there's some risk involved. And so, but we can do it computationally or optically or through the Oz platform. So in a dichromat, some dichromats might look like this, where they have no M cone class, no green sensitive cones. But we could just take a subset of their L cones. All right, it's just a sign. We're going to play God, and we're going to computationally label those as M type. And then we can stimulate them as if they had a different spectral sensitivity, and then present images to that subject. And so I'm just showing it as a dashed wavelength, but we could play them as though we could send sensory inputs to that dichromat's brain as if they had three cone types. And the question is, would they be able to differentiate red from green? Yes, probably. We've already done experiments where they can show that. Do they see a color? Do they develop a sensation of red and green like all the color normal people in the audience have? We have yet to find that out, but these are experiments that are underway. The big overarching question is this, and it's a question that really nobody knows the answer to. If you were to send new sensory inputs to the brain, is the brain plastic enough to generate new percepts to attribute to them? Or are they kind of baked in at birth? Or is it that if you're too old, you have not enough plasticity to use new sensory inputs? We don't know the answers to that, but we have a unique tool to ask those questions. And not just for dichromats, we think that we see color. Everyone thinks they see color normally, like we see all the colors. They're all there. We see all the colors of the rainbow. Well, that is absolutely not true. We see just a sliver, and what sliver we see is greatly impaired by the constraints imposed by the three cone types that we have. And so the green part of the rainbow is not as green as you might see because you're spectral overlap. And by the way, the human optical system is very transparent up to the near infrared, all the way up to a micron, yet our visual sensitivity stops at about 700. So imagine you were born with an infrared cone type. Let's say you were born with a new cone type that was sensitive to, say, 700 or 750, a fourth cone type. Well, it seems to me that if you were born with that cone type, your brain would have been obliged to attribute a color to that part of the space. Why not, right? Moreover, with four cone types, the ability to differentiate different spectra, it's not only extending the color space, so the rainbow would go beyond red a little further, because that light's getting into your retina. Not only would you see extended spectrum, but you could use the information from the four cone types computationally to extract orders of magnitude more, differentiate orders of magnitude more spectra in the world. So the world is comprised of spectra. We take those spectra and we calculate what colors to attribute to the spectra, but we're very limited in the number of spectra that we can differentiate. If you had a fourth cone type, that would go up by orders of magnitude in ways that are even hard to conceive. But we can do this. We could just computationally extend the color space and computationally play a set of cones as if they were sensitive to the infrared, and just ask the subject what they see. So this is what motivates our experiment, and hopefully this is why we can convince people that it's not a colossal waste of money, because it's I think it's an interesting experiment to ask questions that are really have been difficult or maybe impossible to ask until we had this platform. So thanks for your attention. Of course, I'm representing the work, but I don't know how to do almost all of the stuff we do in the lab. That's the domain of engineers and software and electronics people. We've had a lot of people doing science with the systems in the lab, a lot of people doing engineering. It's also very expensive, and so we rely on a lot of funding, specifically for this experiment from the Air Force and from the National Eye Institute. So thanks for your attention, and happy to take questions.
Thanks. I'd like to ask you to say a little bit more about what you spoke. Subjects would be training their brains for some long period of time, and then they would start developing differentiated reactions on different cones.
Well, we don't know the answer, right? So we don't know how long it'll take. Here's one thing I know, that and we've already shown some of this. It's unpublished, and we don't have I don't have a clean slide deck to show it because it's really work that's really underway. If we play the retina as if it had another cone type, are able to differentiate patterns by using those cone types. In other words, they might, but they're probably not at the onset. They're probably not just immediately creating a new color. And so we're showing, we can basically replicate the monkey experiment, and you don't have to necessarily see a new color to do the task. So, but we have no idea what or how long or whether, if exposed to these sensory inputs long enough, that you would actually generate a color in that sense, the quality of a color to attribute to that new signal. So we don't know whether it'll work. We don't know how long it'll take if it works. So this is all sort of unknown territory. I'm willing to spend as many hours as it would take in a bite bar to find out, but I've spent many already. But we're embarking on these experiments, but it's really unknown territory. Yeah. And we don't even know exactly how to train. What are the optimal ways to train new sensory input?
Hi. This is really interesting. So, my question isn't maybe terribly well formulated, but I'll try to pose it, which is that my understanding, and I believe that if you ask people when they perceive a pure red, they can answer that question, and you can reproducibly do that experiment. And it's not the result of a single wavelength. You have to mix some blue, I think, in or something. So there's and this is sort of support for the viewpoint of an opponent color system. So if you add a fourth color, what happens to the concept of the opponent color system, like physiologically or perceptually?
Part of the opponent color system is there are cells in the retina already. There's processing that generates signals that are proportional to the red versus green difference, for example, right? So opponent color system is we can differentiate. There's a opponent process that calculates the difference between the reddish and the greenish excitation, and so that signal gets sent to the brain. Now, whether or not you would just confuse it by adding a fourth cone type, or what would happen if you added a fourth cone type, is there would be the opponent color signal would occur because it's just a neuronal calculation that happens in the retina, but now there would be opponent color signals between what I call L prime and M and L and M. So we would just, so in one experiment, we would just take a subset of the L cones and play them differently so that there would be sort of two channels of opponent color signals sent to the brain. So the sensory signals that would reach the brain would definitely 100% inform the brain about a fourth cone type. And then the question is, how baked in is the brain is it able to now start to appreciate the difference between those two, that additional opponent signal? I hope that's clear. So it doesn't. I think it's compatible with the component color theory, but it's really about the question is whether the brain would make sense of that opponent signal or not. Yeah.
Hello. I thought this was a great talk. My question is also not very well formulated since I'm new to I'm not in this field, but it seems to me that you are enabling color perception by shining or by allowing the subject to be illuminated under like structured light conditions.
Yeah.
To me. So, and it's within your control to shine whatever structure of light you want. So, number one, the perception is dependent on what structure pattern you shine, but also what the internal mosaic the subject has.
Yeah.
So my question is, why stop at trying to get a fourth color perception instead of just, you can shine whatever structures you want, so why stop at 4 and not go even higher? And number two, like, is there any way to know whether multiple subjects will have the same perception with this types of structures, with a consistent set of structures, or do you have to tune these structures for different people?
Well, there is really no limit. I mean, it's natural to just add one, keep the sensory inputs simple, right? But we're not limited by the number of cone types we can simulate or how we would simulate them. We don't really know how subjects would perceive them, but we don't know how anybody perceives anything anyway, right? Except that color is color, I think we can all agree that color is a uniform property that we ascribe to a surface. And it's kind of the uniformity that makes it color versus just some inferred spectra from a luminance variation. And so, but the last comment is that we can also manipulate the cones however we want. And in fact, we're not constrained to do color experiments with these types of manipulations. But I could, in fact, Hannah Doyle, one of the first authors on the paper, is doing experiments where she's just simulating cone dropout. And there's a lot of diseases where you might lose half of your cones. And some of these patients still see 20/20 on an acuity chart, but they've lost half of their cones. And we're interested, well, that's good for the patient, but not good for the patient in the sense that the doctor might not know that they're degenerating at this rate. And we're testing, so we can model whatever or simulate whatever sensory inputs we want to the brain. Okay. All right.
But I know there are a lot of questions, and I also have stuff on the agenda, so maybe I'll say he doesn't late.
Yeah, I'm actually, I apologize, I'm leaving around noon today, but I'll be back on tomorrow and the next day, all day. So if you have questions and you can't find me, you can find me tomorrow. But always happy to answer questions or chat. Thanks.